Hello, 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 hello. Yes. Okay, so good morning, everyone. Myself, Rahul, and it's been an honor for me standing here in front of you. Today, we are giving a talk on the topic named as Exploring the Sun Earth Connection through Starlink event. And I'll briefly tell you about the introduction and I'll briefly tell you about the table of contents first. So we will move on to the introduction. What is the Starlink event? We will do the case study, and then we will see the solar surface. Then we will go on to solar corona and heliosphere, and we will briefly summarize the events that happened, and we will summarize the case studies. So let's see the introduction. So this guy, this poor guy, as everybody knows, sent from Falcon 9 rocket from Cape Canaveral, uh, launched his satellites for the Starlink event. So at 6:13 Universal Time on 3rd of Feb, SpaceX launched 48 Starlink satellites, and unfortunately, the launch took place during the minor geomagnetic storm, which leads to havoc in the density of the atmosphere, and that's why it leads to a collision of the Starlink satellite and ultimately dragging, and around 38 satellites went off. So according to SpaceX, they have released their article that atmospheric drag increases up to 50% higher than previous launches, and it was experienced in the staging orbit, and that's why it leads to a collision. Now, these are the Fortune articles. So Elon Musk ultimately lost around 40 Starlink satellites, as much as $20 million. So how it happened, the nation wants to know. So let's see the chronology of the event first. So we'll go to the solar surface, and as we already knew from the previous lectures for like since 7 to 8 days, that this is the solar surface from where solar wind and solar flares emanating, erupting coronal mass ejections also. This particular thing reached the Earth's surface, the magnetosphere of the Earth, and where the satellite is there, it creates a density fluctuations, a increase in the density, which creates atmospheric drag, and that's why it leads to a collision. Now, to know what happened, we are doing case study of the event through observations of solar surface, solar atmosphere, and heliosphere. Also, we are using simulation results from different data. So let's see solar surface first. So for that, we have to go to sun. So this is the active region. So this is the data taken from HMI intensity gram from the date range, which is from 30th January to 3rd Feb. We have observed that there is an active region AI2936. Also, we are seeing the magnetogram data. Magnetogram shows maps of magnetic fields on the sun's surface. Black and white shows opposite polarity, black which is going away from the sun and white is coming towards the sun, the magnetic field line. There were 6 active regions we have identified due to bipolar structure, verified by integrated space weather analysis system. Also, we have data from the SDO AIA composite, which is Solar Dynamics Observatory, atmospheric imaging assembly. The wavelength we are using is 311, 204, and 171 for the different temperature regions. This is the day range of from 29th of Jan 2022. At night time, 1 to 936, which came as halo, we have observed. Also, we used Happy timeline data, HAPI, heliophysics application programmers interface. So here, as you can see, this is the ideal solar flare cover spike which we are observing on 29th of January midnight at 11:40. So there's a peak observed also. So we are connecting the dots. Now we have concluded from these data that the active region AI2936 is responsible for solar flare. Now we have to see whether there is CME event also happened or not, coronal mass ejection. So we will see what are CMEs and how it happened. So Aryan will tell about that.
Hello, hello. Okay, so I will explain CME briefly. So basically, these are large expulsion of plasma and magnetic field from the sun's corona, and they travel with a speed ranging from 200 kilometer per second to like 3000. So they are very fast, and they are the major space weather driver. So here is an image of CME. This is a classic three-part CME. Here we can see a filament, like it is a core here, and there is a cavity and then a leading edge. So this is a CME. So during the case study, we counter few questions. So here are some questions we can ask. So when the CME first appear, so here's the data. This is the data from Soho Lasco C2. We can see a CME evolving here like this. And this is the time when the CME first evolved, 29 Jan, like around 11:36 in the night, and 2:30 Jan around 2:24 in the morning. So you can see a CME here. And this is our next question. Are all coronagraph images consistent? So what do we mean by consistent here? So there are more. So these are the three data of coronagraph. Here consistency means if they capture similar structure, dynamic, and a feature in the same time frame. So here we can see CME in all the three coronagraphs. There, here, here CME and here. So these are consistent. So this is the next question. Was the CME earthbound? So what do we mean by earthbound? Earthbound means if the CME is coming towards Earth or not. So here is the image. Here is a stereo A, and here is Soho. Stereo is at L5 point, and Soho is at L1 point. So during the event, we observed CME to that is coming towards right in the coronagraph, and here we observe a halo. What does a halo mean? Halo means if the CME is coming directly towards us or not. So we can observe a halo and a CME towards right. So we can conclude that it is earthbound, like coming towards Earth. And here is stereo B, but we didn't take that data from this because this was unoperational at that time. It was lost in space. So that was it. So these were the in situ measurement of CME. So next part will Diksha will cover the heliosphere part.
So, as Aryan told that about the CME, now we have to move towards the heliosphere. Heliosphere, first question arises, what is heliosphere? Heliosphere means, as they are written, outer atmosphere of sun, which is formed from solar wind. Solar wind means solar wind create a bubble which is bubble like structure which and it is called the heliosphere. This heliosphere act as shield for the planets from the interplanetary radiations. Since we have seen the mm, signatures of the CME in corona, now we see signatures of the CME and its evidences on the heliosphere. As this movie shows that how it is pointing. So from From here, a crescent moon-like structure is appear which moves towards the Earth. This is Sun and this is Earth. This crescent-like structure, we predict that this may be CME, which appear from it. This whole plot is the solar wind model. Solar wind model. This model simulate and predict the evidences and signatures of the CMEs. Now we move to the signature of CME. In this plot, we see there is change in the polarity of the magnetic field line. This shows that there occur the CME, and the arrival of the CME is on 3 Feb. From here, Jawahar will introduce.
Good morning, everybody. Good morning, everybody. As Diksha showed, the magnetic field strength plot, we can have some questions for regarding that. What solar angle of the heliosphere affected by the that's observed at burn CME? Okay. From that, solar angle means, as you already know, but the CMEs appeared from the using Enlil model. We found it the CMEs on the western 24 degree and eastbound 5 degree. You can use this to use this Enlil model too. You can find the solar angle. So we get these some plots. You can see the proton density when the CMEs arrived at the in situ area. The density around February 3 is before February 3 this is normal, then on the February 3 around 8:45 UT the proton density is increased. Okay, this shows CME. Then we go to the bulk speed. Bulk speed means the velocity of the CME on the time scale to be taken for that 5 days. On that February, when the CMEs reach the in situ region, the bulk velocity also increased there. The blue one shows the discover data, and black one shows the AC data. AC means advanced composite explorer, and discover means deep space climate observatory. Then this is the temperature, ion temperature on the time. So these also some variation there. You can see the black is the AZ data. It's higher on the day. So shows the CME traces. Then it goes back. Okay. Yes. We seen the inset model later. It shows the estimated time of CMEs arrived on February 3. So this is the Enlil model. Enlil model is nothing but that is a large scale prediction model of solar wind. In the name of Sumerian god of wind and storm. It shows the density and the radial velocity of that CME. On the February 2, you can see these simulations on February. On the February 2, the highlighted one, you can change in the density and the velocity. As you know, the density when the CME toward the Earth, it pushes the plasma towards the Earth, so that has some density, and the CME has some velocity towards the Earth. So that Enlil model simulates that CME, and the arrival time of the CME is estimated the February 2. Okay. Then again we go to the inset data. how does the CME change the global magnetic structure of the heliosphere? When the CMEs are earthbound, the in-situ measurement of as the Dixas showed the magnetic field strength. You can see the first plot. This is a magnetic field strength data of the yellow one is the discover, and the black one is ACE, and the red one is there are two things to now before to understand it. There are two things there. There are two things, the B is component and BT component. BT component means the total interplanetary magnetic field strength, and BZ means the Z component of the interplanetary field strength. That means the BZ means the CM is in the Z component direction towards that means earthbound. When this is the magnetic field strength, when the CM is appeared on that February, around the you can see that the decrease in the magnetic field strength. That means when the BZ component decreases in negative, that means the magnetic field strength is reducing. So that means there's that solar wind affected that magnetic field on the time. So the estimated CME created the geomagnetic storm in the geometric field. So this is the DST, the disturbance storm time data. You can also see on that highlighted on the day, there is a rise in the velocity and drop in the DST. DST also the magnetic field strength. That is the some of, there are many indexes, the KP something and that thing, but just we use two things of that. The main thing is the inset arrival time of base February 3, 8:45 universal time, and but the simulated arrival time of the time is February 3. We simulation shows the 1 day before the data. Then summary from observations, we found that active region 2936 is observed on 29 January, and the coronal mass ejection is heading at 13 January when this erupted. Estimate date of arrivals February 2, and simulated arrival time of CME on February 2. Exactly, we simulated on the time 13 UT, and in situ arrival time of CME is at the L1 point is 3rd February 8:45 universal time. So then BZ count of AC L1 point is 2 February 16 universal time. On the time, the magnetic fields, you can see minus 18 nanotesla. Nanotesla means the field strength. Then the reduction in magnetic field strength. Then the AC discovered proton flux density increased to up to 41 centimeter cubic in February 3. So you can see it comes like a timeline. Then the on the L1 point, the velocity up to raised to 580 kilometer per second on February 3 to February 3. That means here the main thing is the magnetic field strength is decreased, then the velocity increases. That means you can connect with this. Actually, the CME is not much stronger. But how the Starlink satellites are this has happened, the satellite drag force. You know the this is the satellite drag force. You can see the density increases. So here drag force equal to CD is the drag coefficient, a cross section of the satellite, rho is the density of the atmosphere, V is velocity. So velocity is increased and density of the atmosphere increases. So the drag force increases. The satellite falls from its orbit and collide with other satellites. Then the satellites fall into low Earth orbit. So due to the due to the solar wind, the density increases in atmosphere that leads to this around 88 out of 48 satellites, disaster under time.
Okay. I think
Yes.
you all can stand together and then we can have questions. Questions for the team? If you don't ask, then the mentor and I have to ask the questions. It's up to you. So I'll ask a question first then. So you mentioned that CME created the drag force, right?
Yes.
So does all CMEs create the drag force?
No, not all CMEs track the drag force. When the CM is creating the solar wind towards the Earth, when it interact with the magnetic field, then the change in the density and velocity defines that drag force actually.
Okay. So in the formula you have written here, what
Yes.
is V again?
This is the velocity.
Velocity of?
Velocity of the that solar wind.
Velocity of the satellite it is.
Yeah, satellite.
It's not the solar wind, not the CME, it's the velocity of the satellite.
satellite.
That will determine the atmospheric drag as well.
Yes.
Okay. All right. So I think that any more questions?
You talked about the decrease in magnetic field. Did you check if what caused the decrease in the magnetic field?
Because the plasma particles enter the magnetic field, the negative magnetic field strength react with a global magnetic field. Then it is opposite one now. Then it creates that differentiation.
So we are measuring in situ data. So as we have observed in the graph, there is a dip in that. So there is a change in polarity. That's why it falls as negative.
So the magnetic field is observed by a
By-
spacecraft
Yeah.
inside. Thank you.
More questions? Mentor, you want to ask the question?
I mean, can you summarize in 5 lines what you learned from this project? Any one of you?
So yeah, so we have learned from this case study that how CMEs and solar winds, solar flares are important, and we have to see the space weather predictions. We have to do a lot of work in this. They are like it's a future scope for everybody because we don't know. Like this is a $20 million project. We have lost it. So if like we have to see and we have to predict at the real time how CME is appearing. So that is a question mark for us because the prediction time at present is very less. So at real time, if we started to take care of this measure, so we can save a lot of money, and the satellites also we can around 38 satellites gone lost. So we can prevent that if we have the better model for the predictions. So I think we have to do a lot of work on the prediction part and to understand the solar surface and the connection between the sun and the earth, how it is related, how it is correlated. This is what we learned.
All right. Any of you want to say something? Maybe you already spoke, so maybe the other two can.
Only one line.
Yes.
That's why we need Aditya-L1.
Okay.
That's right.
So maybe you want to speak something? Okay, that's fine. Thank you very much. Yes.
Thank you. Thank you.
So the next group, who is going next? You have you give him to copy the presentation. You can take a bit behind so that yeah, you want to sit there? Okay, that's fine.
So good morning, everyone. I'm Meenakshi Mandal, and let me introduce you to my group. This is Akshay Sudhakaran, Sachet Upadhyay, and Anurag Kashyap. And Meenakshi Bisht, unfortunately, who is not with us because of...
Take second. Okay.
Shall I start? Okay, good morning, everyone. I'm Meenakshi Mandal, and let me introduce you to my group. This is Akshay Sudhakaran, Sachit Upadhyay, Anurag Kashyap, and unfortunately, Bisht is not with us because of some health issues. So we have worked under Miss Upasana Baveja, who is a research scholar at ARIES here. And the topic of our presentation is coronal seismology of solar coronal loops. So we have divided this presentation into 4 parts, basically. The first part includes the introduction that I'm going to give you an overview of. Then Akshay Sudhakaran will take you through the data observation part, from where we got the data and what we have learned from it. Sachit will cover the methodology part, and finally, Anurag will do the result and conclusion part. So moving on to the introduction part. It's not good. Oh, okay. Yeah. Okay, so the first part is basically what are solar coronal loops. So for that, we need to know what is solar corona. Solar corona is the outermost layer of the sun, and in which we have magnetic field lines. All the magnetic field lines that are closed are called coronal loops, and the other that are open, we call them magnetic field in general. So these are extended outwards from the solar corona surface or solar corona, and they vary basically from days to weeks, and they are changing rapidly. And moving on next to coronal seismology. So basically, coronal seismology is the study of waves and oscillations produced by the magnetic field lines. And that helps us to better understand the space weather conditions. And in general, we can calculate the magnetic field that is produced by those magnetic field lines. And also, we can predict many phenomena happening in the space weather conditions so that we can avoid them. We have used magnetohydrodynamic equations for the purpose of studying these waves, because in the sun's surface we have plasma. So that is why we have used magnetohydrodynamics. And basically they are divided into 2 groups, alpha wave and magnetosonic waves. They differ because alpha waves are transverse in nature, while magnetosonic waves are longitudinal in nature. And further, magnetosonic waves are divided into 2 parts, fast and slow. Fast because in magnetosonic waves, plasma pressure and magnetic pressure are the main factors that drive the magnetosonic waves. And in the fast waves, they are in phase, while in the slow, they are out of phase. So for the next part, I would like to call Akshay Sudhakaran so that he can give you an overview of it.
Okay, so I'll now describe about the just a brief description about the SDO, or our solar dynamics observatory. This is the spacecraft that was used in order to see the solar atmosphere of our sun. So it was launched in February 11, 2010, and its main goal is to understand the physics of solar variations and its influence on planet Earth, basically, right? So SDO hosts 3 scientific experiments. So this is AIA, which is what we will be looking at deeply, and UV variability experiment, and finally the helioseismic and magnetic imager. So just a brief description about AIA is that it's the atmospheric imaging assembly, and we can see that there's 4 telescopes over here, and the goal is to focus on the evolution of the magnetic environment in the sun's atmosphere. So earlier, it was hard to see the coronal features. So the AIA helps in doing that. So because of this, the AIA, it gives a whole view of the solar corona, and in many different wavelengths, which I will show right now. And it also has the ability to have a temporal resolution of 10 to 12 seconds. So that's just the cadence. So yeah, the AIA will produce data required for studying quantitatively of these coronal magnetic fields and the plasma that it holds. So that's why we're using this data for coronal seismology. So here we have the imaging of all the AIA wavelengths and what features, what areas of the atmosphere it shows. So we'll be looking specifically at this one, the AIA 171 angstrom. Uh, this is the one that looks specifically at the quiet corona. And as we go higher, it will show different aspects of our solar atmosphere. Okay, so the data that was given to us was level 1.5 data. So there's a difference. Level 1 is calibrated, but level 1.5 is calibrated and co-aligned. We were given a data cube in which we had to take a frame. So here we see the frame that we took, and the total number of frames in this data cube was 300 frames with a cadence of 12 seconds. So we had a time period of over 1 hour for these frames. Right. So once we get the data, the next thing we have to do is create a movie. And since there are 300 frames, we created 300 PNG files. And from that, we create a movie. And then this way we can see the magnetic features or the oscillations that are happening in our in the solar corona. So how do I? So I don't know if you guys can see it, but we decided to choose this area over here. No, it's doing something else. It's going forward instead of. You have to hold. Okay, so we specifically chose this region. The movie is, there's an issue here. It's working. Okay, so we can see if we look carefully, there's some plasma oscillation going on here. So that's why we put our slit over that region. So we specifically chose that area so that we have an idea of what we can see from this area, right? We can obviously choose better positions, but from what we did, this was one of the regions where the slit showed some like really good oscillations. So Sachit will be explaining what happens after we place the slit. So
So, okay, once you have the slit, now you have the 2 points that are the end points, this and this, and you can clearly see this is the XY coordinate. So once you have XY coordinate, you have the 2 points. You can find the distance between these 2 points. And once you have distance, you can interpolate between these 2 points and have all the points between them. And once you have that, you have a displacement measurement in all time frames. So over here, yes. So once you have a displacement measurement in all time range, you can plot this nice XT graph. So as you can clearly see, this is the decaying sinusoidal wave. This is our oscillation. So once you have this, so you try to fit with the decaying oscillation equation. Of course, unfortunately, we tried our best, but we weren't able to fit the best fit here. But by fitting this curve, we could have frequency of this oscillation. And these, let me tell you that these red dots are intensity points, which helps the program to track the wave. Okay, so this is the, let me go back. So this was the wave which we encountered. And if you go by the Necheva et al. Paper, sorry. Yes. So you can have see this nice plot and the best fit. And from here, you can have frequency, which is the very important in calculating the further calculation, which will be told by Anurag. Once you have this best fit, nice, you can get the frequency. So over to Anurag.
Curve fitting, we get the frequency of oscillating wave. So now once we get the frequency of oscillating wave, we can easily find time period of the oscillating wave. Now, actually, we are dealing with standing wave here. Standing wave, what I mean, basically kink oscillation. And here is the formula for that. Oh, I'm sorry. So here, V is the Elfman's velocity, L is the length of coronal loop, and P is the time period. So length of coronal loop is lies between this range, and time period of oscillation we get from curve fitting. Now, so now here we can also find further constants like density of solar corona from this from this formula. You can see that here n is the electron number density and n is the mass of proton. Here mass of as mass of proton is far greater than electron, so we only include mass of proton for this reason. Once we get the value, oh, I'm sorry. So once we get the value of velocity rho, so we can find the magnetic field lies in corona. So that's it. Now one more thing. Why we are using this formula? I mean, in kink oscillation, we actually deal with fast magnetosonic wave, but this formula is this formula is actually for Elfman wave. Actually, what happened when we observe our observation for large wavelength, we can say that the waves in coronal loop behave like Elfmanic wave. So that's why we use this formula instead of fast magnetosonic wave. Thank you.
Okay, thank you very much for presenting here your work. So as you mentioned the Alfvén waves, so what are the restoring force for the Alfvén waves?
Magnetic force is the restoring. No, sorry. Magnetic pressure is the restoring force in Alfvén waves.
Magnetic pressure.
Yeah.
And other fast waves or slow waves, what are the restoring force?
So fast wave and slow waves, in my opinion, that is plasma pressure and magnetic pressure both.
Okay. But for the Alfvén wave,
only magnetic pressure.
Okay, and magnetic tension, not
sorry.
magnetic pressure. So is it incompressible or compressible wave?
So Elfvén waves are incompressible, while magnetosonic waves are compressible.
Okay, so can you go to the slide where you put the slit in the image? Yeah. So can you tell how you place slit in such a position? I mean, what will be the particular reason for this?
So you can put the slit in any position you want. We just selected 2 points, and then we look at that specific area. We thought this area, this region, would be good enough to show the plasma oscillation.
But this will be on some coronal loop. I mean, the
Yes.
slit should be on some coronal loop.
Yes. So in this movie, we'll see like there's some plasma oscillation going on here.
Okay.
Uh,
It's okay. It's okay. I understand. But what I mean, there.
why
The,
specifically
yeah.
that? Okay.
Yeah.
So so one reason was when I checked over here in these regions in the coronal loops, there would be a lot of the plots wouldn't show. There wouldn't be oscillation, and there's background noise as well. So when we look at this specific region, there was some oscillation, and then when we placed the slit, we got the correct 3D map.
Okay. I'm asking this question for you to think about.
Hmm.
So I mean, why are you placing the slit at particular position? You can place the slit anywhere.
Hmm.
What will happen if you place it anywhere in the coronal loop? Okay, think about that. Yeah, you can answer also.
So, can you play this in particular for me? So if you wait for long enough, it's actually very fine movement. You can see here that this loop is going from here to here, but we have to wait for like 10 or 12 seconds. Okay, fine. So there was some fine movement here. So what happened here is if I can get a laser thing. Yes, wait. Okay. So suppose this is a coronal loop, right? Suppose so if you place slit along this direction, right? Then you will get the XT graph like that, but it will be very faint and faded. The slit should be placed in such a place that it should give them maximum displacement. So the XT graphs are very clear. If you can read in this Nacheva paper, they have three graphs. One is the very faded one, and one they have the very nice one for the comparison. So the slit.
Yeah, I got it.
So when you were fitting the decaying sine graph in the XT map, so I want to ask, like, I mean, it was explained. So what kind of parameters did you consider while fitting?
Okay.
Over there? Like the equation.
Yes, I will. So about this, no? Yes. So equation was like amplitude times e raised to damping times the x is the time into sine 2 pi frequency x plus phase into some offset plus some offset.
So like overall, how many parameters are there? And after fitting
five parameters.
5 parameters. And after fitting, what kind of results you get from
Yes.
fitting?
After fitting, I am concerned with frequency because from frequency we can get time period, and from that you can calculate the velocity of sanding, which is necessary for the further calculation of magnetic.
Okay. So I had one question to ask. You people said that you used MHD equations, right? So which MHD? Is it ideal or resistive? Which MHD equation did you use?
MHD equations, no.
She spoke. You used MHD equations, right?
Yeah, I mean, we actually observed them using the MHD. We haven't particularly used MHD equations like in calculations and everything in this.
Yeah, but you have any idea of which kind of MHD assumption is used?
Yeah, I think it is ideal. Like we are mostly concerned about elephant waves here. So in my opinion, it is ideal.
And are you aware of what are the assumptions of ideal MHD?
Let's not get too technical. It's fine. So I think I have done a good job. Let's thank them again. Okay, the next group, please. नेक्स्ट नहीं आपकी हो गई ना इसमें थी नेक्स्ट किसकी थी Check the pointer to the top button. If you hold, you will see the on the screen on the work. This is forward and this is back. Okay. Okay.
Hello everyone, myself Parmeshwar Devangan. My team members are Abhay, Niranjan, Yamini, Satyam. Satyam is unfortunately not here due to some medical urgency. So we worked under the guidance of Ms. Jyoti on characterizing CMEs using J HelioWeaver tool. These these are outline of our presentation. First, we'll talk about the solar corona, then CME, then necessity of the same, the classification of CME, and about the J HelioWeaver tool, and then outcomes of our analysis, and then differences and conclusion. Yeah. So solar corona, it is the outermost layer of the sun's atmosphere. It starts from 2100 kilometer above the photosphere, and it mostly comprised of extremely hot and ionized gases. Its intensity is million times lesser than the intensity of the photosphere, and but its brightness, and so that's why it is very hard to observe in normal circumstances. We observe it in during solar eclipse, but we are not dependent on the moon. We can always create our artificial disk to observe the corona every day. And we can classify solar corona in different types. So first is the K corona, which dominates in the inner part of the corona. So what happens is light coming from the photosphere get scattered from the electrons present in the corona, and then we observe the spectrum, which is K corona. And the F corona is the scattering from the gas present in between the sun and earth, and it dominates in the outer portion of the corona. We also observe emission lines from the corona, which is observed in X-ray and extreme ultraviolet rays. But its contribution to the total brightness of the corona is very little. So next part is the coronal mass ejection. Yamini will continue with this slide.
Okay, so I will be talking about the coronal mass ejections. So CMEs are the gigantic expulsions of magnetized plasma from solar corona into the heliosphere, which are primarily caused when the magnetic field lines of in a plasma, they rearrange and reconnect with each other to release large amounts of magnetic energy. In this entire process, billions of tons of matter is released into space with a huge range of velocities from few tens of kilometers to thousands of kilometers per second. So being said this, I'll say that sometimes a CME can happen in a few minutes, and sometimes it can even take many hours. So now talking about the structure, it has a three-part structure with the It has a three-part structure with a dense and compressed structure at the top. This is called the leading edge, and then we have a less dense. Then we have a dark and less dense part in the middle, which is called the cavity, and a bright central structure, which is called the core. Here it is. Okay, so now we'll discuss about why is it so important to study about the CMEs. So the major motivation behind studying CMEs will be because they are the major drivers of space weather. CMEs can create geomagnetic storms when they come in contact with the Earth's magnetosphere. Here we have we have magnetic field lines coming from the solar atmosphere, and then on this side we have Earth's magnetosphere. So when these two come in contact with each other, it leads to geomagnetic storms, which further impact Earth on various levels. Like it do many technological malfunctions like electrical grid blackouts and GPS system failures. Also, the high energy particles which are associated with the CMEs, they lead to electronic disruption in satellites and spacecraft, which pose a risk to astronauts. And also, apart from this, the CMEs can they can produce auroral displays. So the study of CME kinematics can contribute to improve our current ability for CME forecasting and hence mitigate the effects of space weather on Earth. So the next part being classification of CMEs. So CMEs are classified on the basis of two factors. The first one being their angular width, which can be measured with the help of a coronagraph image. So on the basis of angular width, they are classified as narrow CMEs, normal CMEs, and wide CMEs. Those CMEs which have an angular width lesser than 20 degrees are called narrow CMEs, which have an angular width between 20 degrees and 120 degrees are called normal CMEs, and those with an angular width greater than 120 degrees are called wide CMEs. So now we have another classification based on their speed. For this, we consider the backgrounds. We take the background solar wind under consideration. So here we have slow CMEs and fast CMEs. Those CMEs which have speed lesser than the average speed of the background solar wind. Here we have taken the average speed 400 kilometers per second. So those CMEs which have speed less than this, they will be called as slow CMEs. And those CMEs which have speed greater than 400 kilometers per second are known as fast CMEs. Slow CMEs tend to have longer duration, and they have somewhat less impact on the space weather, whereas the fast CMEs, they affect the magnetosphere on a huge note, and they can create huge geomagnetic storms. For the next few slides, I'd like to invite Niranjan.
So in our project, in order to track and characterize the CMEs, we have used the J-HelioViewer software, which is jointly developed by ESA and NASA. This software allows us to view solar features and events in 2 dimensions, and basically allows us to track their evolution over time. So the image on the right is a basic interface of J-HelioViewer, and you can select the start and end date of any particular event, and then choose the instrument you want to select to visualize the events. It also has to visualize and record movies as well. So we have used J-HelioViewer to obtain basic parameters of CMEs, and we have tracked how they evolve to get to characterize them. So the basic parameters are height, which is the radial distance from the center till the edge of the leading edge, which we obtain from the J-HelioViewer interface itself. If you can see here, the row tells what distance the CME is when we put the cursor at this point. The central position angle is basically the angle of the central part of the CME measured from the north in anti-clockwise direction like this. Angular width of the CME is the angle between the two position angles as illustrated here. The velocity and acceleration of the CME we determine by obtaining the how height varies with time and plotting them. So in this project in JHelio Viewer, the data source for our project is mainly LASCO and EIT, which are two instruments on board the SOHO mission, which was launched in 1995 and is orbiting in a halo orbit around L1. LASCO stands for Large Angle and Spectrometric Coronagraph, which has three major coronagraphs, C1, C2, and C3 with varying field of views. C1 has a field of view of 1.1 to 3 solar radii, C2 1.5 to 6 solar radii, and C3 3.7 to 30 solar radii. Unfortunately, C1 is not working right now, but C2 and C3 are still functional, and we have used both of them. Another instrument we have used is EIT, which is Extreme Ultraviolet Imaging Telescope, which is sensitive to a few particular wavelengths, which helps us to image the corona and transition region on the solar disk up to 1.5 solar radii. So the EIT image is what you see in the middle in green color, and the red portion is from C2 coronagraph, and the blue portion is from C3 coronagraph. Now I'll hand it over to Abhay to discuss the analysis and results.
Hello everyone. We'll start with the analysis of our first event. First, I'd like you to put your focus on the video here. We have made it a bit slowed down so that you can see it a bit more clearly. As you can see, the CME, here we had the central edge. These are the sides. And then we measured its height as Niranjan had explained. And then we plotted the points as shown here. This is the scatter plot. You can see the X as the points we had. Then we linearly fitted a line, and the equation of the same you can see at the top, which is y is equal to 568.224x plus 199.424526.970. Here, y is our height of the CME, and in the graph, you can see it as measured in solar radii, and the time is measured in second. Here, we have changed the equation so that it comes into kilometers. Y is in kilometers. Similarly, and when we differentiate y with respect to x, here x, the x-axis is time. So it gives us dy by dt, which will be equal to 568.224, which will give us the average velocity of our coronal mass ejection. And in the second equation, you can see it's a quadratic equation. We have done quadratic fitting with the same points, and by double differentiating it, we can get half the value of acceleration. If you are all aware of how derivatives work, then we'll move on to angular width and time. We have measured the angular width as Niranjan had explained by subtracting the two angles we got from the JHelio Viewer app. As if you can remember the CME, there was a small solar event which is known as flare. It happened after the CME started. So there was a slight deflection in the CPA, that is the central position angle. Otherwise, in normal CMEs, we see that the angular width is usually a constant, or it increases but very slightly. Here in this CME, we have a slight deflection of central position angle, and which also caused a slight decrement in our angular width versus time graph. Then we have measured instantaneous, we have plotted the instantaneous velocity versus time graph and acceleration versus time graph. We all know what forces act on in CME, which are the drag force, the gravitational force, and the Lorentz force. As the CME moves away from the from the sun, all the action of these force upon the CME, it gets quite small. And in most of the graphs, we can see the acceleration in the later parts of the graph. It will saturate to 0. Next slide. This is our second event. In the second event, you can see the CME. Here it was accompanied by another smaller CME. And we can see here the deflection is a bit bigger. We can see the velocity versus time graph. All of the graphs that we had, all of the explanation we talked about, they all work here too. The angular width, it slightly increases over time. We can see the distance. If linearly fitted, it is quite satisfactory. we can see the average velocity here is 189.113 kilometer per second, and the average acceleration, half of the average acceleration is minus 0.002. Then here too, we can see that the acceleration saturates with time. This third event, this is a bit, you can say, better. Here you can see the CME is alone. No one is messing with it. And you can see the halo part quite well. Here, the core is also quite clear, and so is the cavity. Here we have got a constant CPA, that is the central position angle. The velocity and acceleration, they'll still change. Here we can see we couldn't really track the CME for much farther from the solar radius. So the acceleration hasn't saturated to zero. It is still 0.05 kilometer per second square, which will be 50 meter per second square. Moving on to the fourth event. Yeah, the video is playing. Here too. Here the CME disrupted quite early. This was not a CME which was quite stable. It disrupted quite early, and here too the acceleration didn't really get time to saturate. We can see the width and the CPA. They followed the data that we had talked about earlier. We can see all of the graphs here. The speed of the CME here was 316. And as we remember from Yamini's talk, she told us about fast and slow CME. This is a slower CME since its average velocity is slower than 400 kilometer per second. Now we will move on to the summary. Here we can see the central position angle, the final central position angle of the CMEs, the average velocities of the CMEs in kilometer per second, the average acceleration of CME, and their classification. We haven't really put in if they were a narrow or wide CME, because all of the CMEs that we tracked here, they were all, if you really put your attention into it, they were all a normal CME. They were not really narrow. They weren't smaller than 20 degrees, but none of those were wider than 120 degrees. Now moving on to our conclusions. We used the J-Helio Viewer tool and successfully tracked 4 CME events using Soho LASCO CME data. We investigated the evolution of CME's leading edge by measuring its height, which gave us the velocity and acceleration. We also measured the angular width and CPA, that is the central position angle again. We found 2 fast CMEs with average speeds greater than 400 km per second. All of the CME that we tracked, they were of normal width, and we observed a consistent linear increase in the height of CME, other than the deflections. And if we see all the graphs again, we can see the linear fitting was quite satisfactory. These are the references that we used. And thank you all for being here. Any and all questions are welcome.
Yeah, so I have here over here. So I have 3 questions overall, like in different slides, I guess.
Yes.
So when she was mentioning about fast and slow CME, she mentioned something called background solar wind. So I didn't understand what you mean by background solar wind.
Background solar wind means the general solar wind, because the magnetic field lines that are coming, they have some resistance. The background solar wind will resist that. So in comparison to that background solar wind, we classify them.
So is it based on the distribution of the wind or the direction? What classifies it as a background?
Like it's just the normal solar wind. We are just comparing it with how it is, because drag force acts on the CMEs based on its velocity. So if it's like higher than the average solar wind's speed, then it will like get decelerated, and in the other case it gets accelerated. So we are comparing it with the average solar wind velocity to just classify how it will be.
Okay. And okay, second question is where you mentioning central position angle.
Yeah.
So it wasn't mentioned what it actually is with respect to what axis and what direction is the angle measured, the central position angle.
Yeah. Sorry, I couldn't.
Central position angle, the CPA.
Yeah.
So what with respect to what axis and in what direction is it measured?
If you can see, I had mentioned it's measured from north. It's like marked
With
there,
respect to
and
solar
and
north.
and it's measured in anti-clockwise direction.
Anti-clockwise.
Yeah.
Okay. Thank you. And the graph where you were showing the height time plots, I just had one doubt regarding that. Any graphs you can open, like those scatter points that you plot?
Yes, sir.
What are those scatter points? Like, where do they come from?
These are the points that we got from the JHelioView app. It tells us which solar radii we are at and at what time.
I mean, what I mean to ask is, how are those points selected? Like, is it a track point across the CME or what?
Yeah, it is the leading edge point. As we
Leading edge
talked,
point,
yeah,
okay.
the height from the center of the sun to the top of the leading edge. That will give us the height, and all of the points are taken from that.
Okay, okay. Thank you.
Yeah.
So there you have used two equations there, right? So like
Yeah.
it's just a trial, or like how did you use those?
No, these are just simple linear fitting and quadratic fitting. I haven't really shown the curve of quadratic fitting because it was looking quite chaotic. Otherwise, we have just used simple fitting programs, and we have just linearly fitted the curve to get the value of average velocity. As we can remember, it's y is equal to mx plus c. We only need we usually use the best fits when we do experiments too, right?
Right.
Yeah. So here we have used two best fits. One is to get the value of average velocity, which will be the linear fitting.
Okay, and for acceleration, the quadratic. Okay.
Okay, I'll ask one. So
yes, sir.
Imagine CME coming from the center of the disk towards
sir.
the Earth.
Yes, sir. Yes.
What would be the angular width?
So it will be 360 degree. It will be a halo scene.
Okay. I just want to know your understanding. Any more questions? Okay, let's thank the group again.
Thank you, everyone.
Who's going next? You're going next, right? You can take the Zoom link or copy your presentation. No, I'm asking the next group.
Just wait.
Let him sort them first and after.
आप भैया स्टॉप रिकॉर्डिंग करें.
Stop sharing.
You have to place the number. 1 second.
When your turn comes, you can ask. Oh, same group? No, okay. No.
Yes, transport classification using this. Yeah. Okay, 1 second.
So, good morning, everyone. Myself, Nagashri, and I'm here with my team to present our project work on the topic sunspot classification using a clustering algorithm, DBScan. So, our team members are Arjun Kanan, Nutan Patni, Sambit, and Karthik. And unfortunately, Nutan isn't here due to her PhD interview here at ADS. And our project mentor is Dibya Mishra, who is a senior research fellow here. So here is the outline of our presentation. We'll be starting off with the introduction of sunspots and then methodology and their corresponding results. So starting off with what are the sunspots? So sunspots are these dark regions on the sun who's having a higher intensity, higher magnetic field strength, which whose values varies around 3 kilogauss. So they usually appear dark as they are as the temperature is very less compared to that of their surroundings. So they usually occur in pairs and they are bipolar pairs and having opposite polarities. So they have these two very distinct features. One is the umbra, which is the central inner central part, and other is the penumbra. So the umbra region is around 3000 Kelvin, and the penumbra region is 5780 Kelvin. And here is the sunspot classification. So basically, sunspots are classified based on their size, and their magnetic properties, the polarity. So the type of sunspots doesn't show any kind of bipolarity, and they exhibit penumbra. And B type show polarity, but they doesn't exhibit penumbra. So C type and D type both shows bipolarity, but in either case, in C type, either the leading or the trailing spot has the penumbra, and the D type doesn't have. So the data for project work is obtained from Solar Dynamic Observatory, which is a space mission launched by NASA to study sun. In this project, we'll be using HMI data, which stands for Helioseismic Magnetic Imager. So this captures full disk images of sun with 45 seconds of cadence. The three data sets of HMI include the magnetogram, Dopplergram, and continuum intensity. So in this project, we'll be using continuum intensity images, which produces images at the wavelength of 6173, which is iron neutral. And this is the methodology, and Ayush, Samit will be.
Hello everyone. I will be explaining the limb darkening part. So limb darkening is a phenomenon of decrease in the brightness of the star when we move towards the periphery. So limb darkening increases due to when we increase the radius due to the decrease in the gas density and the shorter line of sight through the star, and the dimming gradually decreases to zero towards the apparent edge of the star. And as you can see, it's showing some limb darkening towards the edge of the star, and in the graph of intensity and pixel, it's showing an absolute zero towards the apparent edge of the star. But when we do some limb darkening corrections, so we remove those limb darkenings, and you can see clearly in the graph that it's showing it's not getting zero towards the edges of the star. And to further explain threshold I'm asking, I want to invite my friend Karthik.
Hello. I'll be explaining about thresholding and masking. So now that we have corrected for the limb darkening, as Sambit explained, now we are ready to detect where the sunspots are in the solar disk. So here we use threshold algorithm, saying that now we have the uniform intensity all over the disk. Now we can use the threshold algorithm, saying that if the spot if a pixel has such a intensity, then we consider it or we not. So now by thresholding, we'll get the spots and noise included. Now we use appropriate algorithms to remove noise and make a binary image of it, which is called masking. So we use algorithms like CANI, edge detection, closing, erosion, and dilation for noise removal and making it more apparent. And then we use some appropriate conversion techniques to map, to reduce the area of the sunspot with the image. So this is the thresholded image, and this is the masked image. Thresholding image, it's a continuous image, 0 to 255. So masked image is a binary image. It's only 0 or 1. And now I invite Arjun to explain the DB scan algorithm.
So hello everyone. So I'll be talking about the main part of the project, which is the clustering algorithm. So first things first, why do we even need to cluster the sunspots or group them in the first place? So we need to do that because in the solar catalogs, everywhere we see, they report numbers as sunspot numbers and sunspot groups. So as Nagashri had explained before, there are multiple types of sunspots, right? So if we classify them as groups, we'll be able to classify whether they have an umbra or a penumbra very clearly after doing the clustering algorithms. So we'll be employing the clustering algorithm called density-based spatial clustering of applications with noise, abbreviated as DB scan. So as you can see in this image, the two most important parameters that's required for this clustering algorithm are N, which is the minimum number of points in a cluster, and epsilon, which is, let's say, a distance metric. You can use multiple types of distance metric, but the one which we have used here is your regular Euclidean distance. So you can classify for any given cluster, you can classify the points into three parts: core, border, and noise. So if you can look at this image, this let's consider this point A. So if I set the minimum points as 3, right? So it has a certain radius. So if all of these 3 points fall within this core, then this thing is considered as a core point. And all of these red points over here are considered as core points. Now the next kind of point is called a border point. So these border points are those where it doesn't have a full, like it doesn't have the minimum number of points required inside its cluster, but it can be reached by some core point, which means it's still technically part of the cluster. Now, the last kind of point is called a noise point, which is not reachable from any of these points. So this is one of the main criteria of DB scan. So we applied this on one of the image after doing all of this data processing. So the one in the left is what we got. This is the number of clusters was 8 for this, and this is the reference image showing the different sunspot groups. So as you can see, it matches pretty well. So I'll move on to the final results that we got. So after doing all of this processing for every image, we took data worth of around 7 to 8 years, 7 years. So we calculated the sunspot area for all of these 7 years, and we plotted them across with time. So you can see we started from 2011 and it goes till the end of till 2017. And you can see that the black lines represent the yearly average, whereas the yellow one is the daily data. So as you all know, in 2014, there was a solar maxima. So this peak corresponds to that maxima, which we have verified using the results. Then finally, we took we applied the clustering technique to 1 full year. Unfortunately, we couldn't do it for the multiple years because of computational issues. But we managed to do it for 1 year, and we got a yearly mean number of clusters as 6 around. And in the catalog, it was around 5. So it doesn't match completely, but there can be better techniques to select the parameters and cluster it properly so that we get a proper data set. And if we do it for all the years continuously, we can even do a correlation between sunspot area and, let's say, the number of clusters, so that for completeness, for the sake of completeness. So, yep. Thanks.
Yeah, hello. So I had a very basic question about regarding sunspots. Why the temperature is low corresponding to the surrounding?
So there's a equilibrium condition that needs to be satisfied. So the magnetic pressure and the plasma pressure has to be balanced. So in this around this sunspot inside it, the magnetic pressure is higher. So in order to maintain that equilibrium, plasma pressure is lower, so less gas is present over there, less energy. So that makes it darker in a nutshell.
Okay.
You mentioned you corrected for limb darkening. How you did?
Initially it was it's a empirical formula which you saw the other day. Someone explained it. It's a empirical formula, but here we use a 5th-degree polynomial to correct it, which is a function of the wavelength. So with an appropriate coefficients to each of it. So that's how we corrected it.
Just to add on to that, so the basic thing is we have to get the radiative transfer equation, which has a source function. So that doesn't have a closed form solution if you integrate along the optical depth. So we have to assume some like linear or quadratic or some polynomial function, and then once you solve that, you will get the equation of limb darkening, and then you can correct it by dividing each pixel by that value.
You mentioned there is some N was there, no?
In the clustering.
Yeah.
Yeah.
So what was that?
Yeah, right. So this is like the minimum number of points that should fall within an epsilon distance so that it can be considered as a cluster within the core point.
So in 10th slide, 10th. Okay, go above. Yeah. So is it a part of sun that you have selected or?
Yeah, it's a part of the sun. We have excluded the limb
Limb
because of
part.
projection effects. Yeah.
Yeah.
So you analyze sunspot area. Why is that? So why not sunspot number?
So you can actually do both. But sunspot number, let's say if there's a very big sunspot, then that will be considered as just one in the clustering. But the area, so you have to basically do both for completeness sake. Yeah.
Yeah, I mean, what I want to know is what is the scientific significance of selecting area instead of number? As in, if there is any?
We actually confirmed the data with the actual website. So there was area given in the website. So we were just relating it, like how correct our method is. And it's just a detection thing.
Okay. Okay, so just wanted to ask you that the sunspot area that you have classified, that's a marker for solar activity, right? So what is this specific need of classifying it into all of these different groups? Is there a physics behind it?
So we can. So there were different kinds of sunspots, right? Like A, B, C, and D. So if you classify that, then we'll be able to study those properties clearly, right? So
Which kind of properties? Like,
whether it has a umbra and penumbra and
yeah, but what effect will that have on our knowledge about the sun or the activity?
If it gives off a CMA, how powerful it is, if I'm not wrong.
Well, you're close by, okay.
So when you mentioned about the limb correction, so you told that you assumed a particular polynomial. So what polynomial, what degree polynomial did you choose, and what was the reason behind it?
It was a quadratic polynomial. So that was. Okay. Okay, it was a fifth degree polynomial that we chose. So we chose it based on the complexity. That was the most complex one, so we used that.
Okay, so is there any physical reason or something? Sorry?
Even the quadratic formula would be fine. Like just a bit of corrections would be there towards the end. Yeah, that's it.
Okay, I just want to clarify one thing. Someone mentioned about intensity going 0 because of limb darkening or something, right? Why is it you have showed the plot with the 0 intensities on either side before limb darkening correction, right? You know why is it 0 there outside the limb? Yes, it's not because of limb darkening, but when you're mentioning, you mentioned it is because of limb darkening. But anyway, that's just a clarification. I think let's thank the group again. That's okay. You can discuss later because we have. So I think now we can break for the tea, and after that we can continue with the presentations.